Imagine a 1,000-pound arm of solid steel swinging through the air. Without a way to detect obstacles, that massive inertia transforms a precision instrument into a blind, destructive force. To actually be useful, a robot needs a way to feel its environment. Sensors act as the bridge, translating the messy, unpredictable physical world into the clean, digital signals that a computer can actually understand. At the heart of almost every sensor is a foundational piece of technology called a transducer. A transducer does one specific job. It takes one form of energy and converts it into another. Usually, that means taking physical energy, like the pressure of an object pressing against the machine, and turning it into an electrical current that a processor can read. You use transducers every day. The microphone in your smartphone is a perfect example. It takes the physical energy of sound waves vibrating through the air and converts it into an electrical signal, so your voice can be transmitted. Unless we have a way to convert physical reality into a language a machine can process, robots are trapped in the dark. Without sensors, they are isolated, dangerous to operate, and ultimately useless for complex tasks. The first layer of robotic perception starts right at the surface. Just like us, robots need a sense of touch to know when they've finally made physical contact with an object. Sometimes this is just a simple on and off switch. A bumper clicks and the robot knows it hit a wall. But for delicate work, robots use force feedback. This allows the machine to measure exactly how much pressure it is applying to a surface in real time. If a robotic gripper is programmed to pick up a light bulb, it can't just clamp down at full strength. Force feedback sensors read the rising physical resistance from the glass, telling the motors to stop squeezing the millisecond the grip is secure. Touch requires physical contact. To move faster and operate more safely, a robot needs to perceive objects just before it hits them. It needs a near-field bubble, created by proximity sensors. Inductive proximity sensors generate a small electromagnetic field. When a metallic part passes through, it disrupts the field, registering the object's presence without touch. This lack of physical contact is a massive advantage. Robots can track hundreds of fast-moving components per minute, avoiding mechanical wear. By mastering both the immediate physical surface and that near-field boundary, robots can handle fragile materials and track high-speed targets. They can interact with the world without destroying it. Once a robot understands what's immediately in front of it, the next step is pushing that bubble of perception outward to map the entire room using far-field range sensors. To determine exactly how far away an object is, robots use the time-of-flight principle. A sensor sends out a pulse of energy, like a laser, and calculates exactly how long it takes for that wave to bounce back to the receiver. This is how an autonomous mobile robot navigates a busy warehouse floor. It continuously fires these pulses in all directions, building a live 3D map so it can steer around forklifts and human workers in real time. Beyond scanning the room, machines must also look inward to monitor their own physical condition. Inside the chassis, a network of internal sensors, like accelerometers and temperature gauges, constantly tracks the machine's stress levels. If a robotic arm lifts heavy engine blocks and internal friction spikes, a thermal sensor will detect the rising heat in the motor casing. Before the wiring can melt and cause a catastrophic failure, the sensor triggers an automatic emergency stop. Between scanning the room for external obstacles and monitoring its own joints for internal stress, the robot gains the complete context it needs to survive in a highly unpredictable environment. Having a dozen different sensors doesn't mean much if the data isn't combined. True robotics requires synthesizing all of these separate inputs into a single cohesive picture. You can see why this synthesis is required on a modern car assembly line. It is a dense, high-stakes environment where dozens of massive robotic arms are operating inches away from each other simultaneously. To perform a task like welding a car door, a single robot arm uses a range sensor to locate the vehicle chassis, a proximity sensor to ensure its welding tip is at the exact right distance from the metal, and force feedback to hold the panel securely in place. All of these sensors are firing and adjusting at the exact same time. This constant flow of data also powers a critical safety feature known as an interlock. An interlock is a software layer designed specifically to protect human workers by overriding the machine's programming based on sensor input. If a technician accidentally steps onto the factory floor, the robot's range sensors immediately detect an unexpected shape. The interlock takes that data and instantly kills the power to the motors long before the human is near the danger zone. A machine is entirely defined by the physical data it can capture. By layering touch, proximity, and distance into a single system, we take heavy, blind machinery and elevate it into a fully aware, autonomous tool.
In this session, Module CAT-017 covers advanced circuit design. Don't forget to like and subscribe to stay updated with our latest tutorials.